Hello, it's Keith here, and this is the second in my 6502 assembly programming tutorials. Now, we looked last time at how to do some very simple setting of registers and some basic addition and subtraction, but at this point we do need to go into some quite complex things because on the 6502 the addressing modes are the key to the way the system works. So for simplicity we're going to go through them all at the same time and then we're going to move on to other things. So what are addressing modes? Well, we looked last time at how when we were setting a register we could use a value with a hash symbol, which would be an immediate value that was just loaded straight into the register, or if we didn't use that hash we would load in from a memory address. And these are two basic kinds of addressing mode, but there are many others on the 6502. And these addressing modes on the 6502 are the way that the 6502 gets around its very low number of registers, and it does so very efficiently. And so the 6502 is just as capable as the Z80, even though the 6502 with its 3 registers has far fewer registers than that processor. So today we're going to look at all of the addressing modes one by one. We're going to see some examples of them in use, and so we're going to learn how they work, and hopefully after this episode it will be very clear to you what each addressing mode does. I do have to say though, if you get confused at any point, don't worry too much, because while I'm covering them all in one go so we can say we've covered them, if you don't understand them yet it's not going to matter, because we're going to keep covering them over and over again as this series progresses when we actually come to use them for their practical uses. It's just important that we have the groundwork in place for when we actually see them later so that we can say we understand the concept behind them, and that's what we're going to cover today. So let's make a start. Well, the first thing we're going to have to do is we're going to have some test data set up on our system, and we're going to do that by loading some data into memory. So we've got some commands here that we're not really going to go into, but essentially we're copying some data into certain areas of memory. You can see the default data here, and we're going to use the memdump command to see the result of that straight away. So we're not going to go over this because it really doesn't matter, but let's actually execute the example and see what the resulting memory setup is. So here's the way the memory will appear when we run things. You can see we've got some bytes at the memory address hexadecimal 80 here, some at hexadecimal 2000, some at hexadecimal 1310, some at 1210 and 1B19. Now these bytes we're not going to go into just yet. Most of them are just consecutive numbers as markers, but we're going to see these being used by various examples, and some of the examples need specific memory addresses. So these memory addresses I've selected here are just ones that are easy to show in the example. They don't have any particular meaning beyond that, so don't worry too much about that. But as I say, the important thing to take away from this is we've got test data in specific locations in memory for when we do our testing. So what are we actually going to do? Well, the first thing to understand is that these examples won't work on all systems. Because we're writing to specific memory addresses, some systems like the Nintendo NES, for example, the 2000 range is actually used by the video hardware. So when we run this on the NES, it will crash. I'll just show you that now. That's what happens on the NES. So we're going to be running on the BBC. These are all tested on the BBC. If you're not interested in the BBC, then don't worry, because as I've said before, what we're doing here is theory. We're not looking at the BBC as a system, we're looking at the 6502. So what we're seeing today will work on any 6502 based system in theory, even if these examples will not work on that system. So we're going to use some quite technical names for the addressing, and I don't want you to worry too much about those names. It's just important we use the official definitions. Now, the kinds of addressing you can use with each command will vary, and at this point I would suggest you visit my website and download the cheat sheet, which will show you all of the commands the 6502 has to offer, and you'll clearly be able to see which ones will work with which kinds of addressing mode. Now this is the cheat sheet here. The commands are going down the side here, and across the top you've got a column for each kind of addressing mode with a little description and a sample of how it would work. So if you download the cheat sheet once you've seen this video, and when you start to use the commands, you'll be able to understand which commands work with which addressing modes. And if at any point you forget and you think, oh well, I can't remember what indirect addressing is, that's where you come back to this video to see the examples, and hopefully that'll help you understand it. And that's why we need to look at this today on our second lesson, not later down the line, because we're going to need at least some of these commands very early on, and in fact we've actually already used 2 of them. So the first kind of addressing we're going to look at is what's known as a relative addressing. Now, relative addressing is relating to jumps. This is where we skip over certain commands, and this is used in condition statements. This is something we're not going to cover this lesson. Condition statements are coming very soon in lesson 3, but just yet it's a bit early for that. However, we do want to discuss what relative addressing is. So, well, what is it? Well, here's an example of relative addressing, and what it is it's an offset to the current running command. So in this example here, we're using the branch carry clear command, BCC, and we've already cleared the carries, so we're always going to branch. And what we're doing is we're branching by plus 3 bytes. Now, the 6502 has a register called the program counter, which is the actual running command. And when we add 3 to that, which is our relative adjustment of 3, we are skipping the next 3 commands. Well, this JSR monitor, the JSR command is 1 byte and the monitor address is 2 bytes. So we are skipping the 3 bytes of this monitor, effectively ending up here. So if we just run that, if we look at the result here, you can see there's 2 monitors here. But we've got 3 here, and the reason we've only shown 2 is because we've skipped this middle one because of this BCC3. I can prove this to you. If I change this to BCC0, we've now got 3 because we've effectively not changed the program counter at all, and so we've continued execution on the next line. Now, if we change this BCC to BCC -5, this is going to create a right mess. You see, the BCC command is 1 byte. The value here is 1 byte, and this is 3 bytes. So if we now execute this, we've created an infinite loop, and our machine has crashed. So the offset can be positive or negative, but it has to be from -128 to +127. The reason for that is that's the maximum values that can go in a single byte. So in real cases, we wouldn't actually use a mathematical value here. We'd use a label, so we could do test here. And if I just put test in this position here, and then execute this, the effect is the same, because the assembler has worked out this test label and the offset that is needed to put in place in here to do that offset. We're going to come to labels and we're going to come to branching later. The important thing I'm saying here is this relative is an offset from the current position. Now, if we look at the cheat sheet, you can see the relative here, and it's only used with these branch commands. It doesn't work with any other kind of mathematical statements, but as I say, it is considered an addressing mode by the 6502, so we want to discuss this. As I said though, the branch has to be within 128 bytes. So if I put in DS255, now this is effectively faking in 255 bytes. And if I just shrink this so you can see my assembler output here, it says branch destination out of range. And what this means is offset is more than the maximum 127, so it's not possible. Now, there are ways of fixing that, but I was just trying to make the point that it's an offset of up to 127 or -128. So that's how we can use relative addressing with branching commands. And just to be clear again, we are going to look at this in a later lesson, so don't worry if you don't understand branching yet, because we've hardly covered it. I was just explaining relative addressing. Now, the next kind is very, very easy. The 6502 has something called accumulator addressing. Now, if you remember, the accumulator is a register that can hold numbers, and accumulator addressing means a command that doesn't use anything else except the accumulator. So this is commands that just use the value in the accumulator. And so here's an example of this here. We're going to use the logical shift right command, LSR, here. And what we're going to do is we're going to shift all the bits in the accumulator to the right. This is going to change the number in there. And because this is an accumulator addressing mode, we have no other parameters of any kind. So let's try it out. So here you can see we had the hexadecimal 8 that we loaded into the accumulator and then showed the monitor. Then we did the logical shift and ran the monitor again. Now, when we shifted the bits to the right, we've effectively halved the value of the accumulator. And so that's a good thing to do if you need to know how to do halving. And there is also an arithmetic shift left, which is the opposite command. And we've now doubled it to the hexadecimal value of 16, which is hexadecimal 10. So we can do those kind of commands, and there's a lot of other commands. And as I've said again, just check out that cheat sheet and you can see the accumulator addressing mode and all of the commands that use it. There's not so many, but they do work with just the accumulator, no other parameter of any kind. Next we're going to do immediate addressing, and this is one we've already covered, we just didn't know what it was called. So what is immediate addressing? Well, immediate addressing is quite simply when we've specified a value with the command itself, and that's when we use that hash symbol. So the parameter isn't coming from memory or anywhere, it's just literally coming straight on the command line next to the command itself. So here we've got LDA and an immediate value of hexadecimal 10. Then we've got add with carry and an immediate value of hexadecimal 20. So as I say, we've already covered this one, we just didn't know we had. So it's very straightforward. Nothing to worry about there. Of course, as I said last time, you need to remember to put the hash in because otherwise you will use a different kind of addressing. So now is the one that's really the crux of the 6502 system and how it works with its lack of registers. And this is something called zero-page addressing. I mentioned very briefly last time that the first 256 bytes of the memory of the 6502 are special. They're known as the zero page, and the 6502 uses those as kind of fake registers. It can store values to and read values from that address space very quickly, and that's why it's special, and that's why it's got a special addressing mode to work with it. So if we specify an address below 255, for example this one of hexadecimal 80, this is going to load from the zero page memory address, and we could, if we wanted, actually put 2 extra zeros here and it would do the same thing. So we can now run this, and what we will do is we will load in from the memory address hexadecimal 80, and this is why I've put some special test data in this address here, and you can see we've loaded in hexadecimal 11 from the zero page. Well, what's special about the zero page? Well, the answer is simple really. If we loaded from an address like 1080, this command would compile to 3 bytes, but when we load from the zero page address hexadecimal 80, it's only 2 bytes. It's a smaller command, therefore it's faster. And the zero page registers can do all kinds of clever things that other addresses can't do. So the first 256 bytes of the memory, the zero page, are kind of a premium. That's the special area of memory that you can use to do all the things on the Z80 you would have used the HL or BC registers for. This is where we store all our temporary values, all our addresses, all our counters that won't fit in our normal registers. So they're absolutely critical, and we are going to look at them in much more detail later. But for now, just understand that they're important. We can specify them just with a 2-byte definition, and when there's no hash here, we're loading in from that zero page, not from an immediate value. So now we're going to come to one of the more tricky commands that the 6502 can do, and like with a lot of commands, this is one that you can only do with values that are held in the zero page. So we've got this X and Y register that we've not really looked at with any real purpose before, but they are very important registers, and the X register in most cases, and also to some extent the Y register, are capable of something known as indexed addressing. What does this mean? Well, quite simply, when we specify an address on that zero page using just 2 digits, so hexadecimal 80 for example, we can then add the value in the X or Y register to that address and then read from the result. So looking at this example here, if we load from hexadecimal 80, X when X is 1, we will actually end up reading from the memory address hexadecimal 81 because we've added the X to that address we specified. We can also do this with Y in a lot of cases. Sorry, that's a typo there. That should be hexadecimal 80, Y. If we would load in from that there with Y equals 2, then we would effectively load from hexadecimal 82. We would get the data from that address there. So we can test this out just fine. So let's have a look at that now. So you can see here, we're loading from hexadecimal address 80 plus X, and then hexadecimal address 80 plus Y, and we've loaded X with 1 and Y with 2. And we're going to jump to the monitor in both cases. So let's see the result here. So you can see in this first example here, the A register has been loaded in with hexadecimal 12. Well, this was hexadecimal 80, and the X register was 1, so we are loaded in from 81 here, which is a 12, which is why this has been set here. Now in the second example, we loaded in X, and we've loaded in 13. Well, why have we loaded in 13? Well, hexadecimal 80 is 11, and the Y register was 2. So we've added 2 to that hexadecimal 80 and loaded in from here this hexadecimal 13. So that's how we do this. So we can load in, we can use the zero page as a sort of lookup table and X or Y as an offset from that initial zero page address. Now, I do have to point out that the X version of this is more powerful than the Y version. You can see here the 0-page X version is in this line, and the 0-page Y version has very few commands that it can work with. It can really only work with ones actually using the X register, but they do both exist, so they were worth mentioning. So that one was a little bit tricky, I apologise for that, but we're going to look at a much simpler kind of addressing now called absolute addressing. Absolute addressing is kind of similar to the basic 0-page addressing in that we're just reading directly from a memory address. However, with absolute addressing, we are specifying the full address, so we're using those 3 bytes for each command rather than the 2 if we were using a 0-page command. So here we've got a simple example of an absolute address. We're loading from address 2000 into the accumulator. So this will take 1 byte, this will take 1 byte, and this will take 1 byte. So this is a 3-byte command. And as I said before, our 0-page version would have only been 2 bytes. So it's going to be a little bit slow, but it's still going to work just fine. So here we've loaded in the accumulator from address 2000. And you can see here address 2000 is 1A, so that's definitely worked okay. So well, apart from the speed reduction of the larger command, what is the disadvantage? Well, with absolute addressing, that works fine. But we don't have as much power as the 0-page, and we will see that in just a moment. So as well as absolute addressing, we can also use X and Y as an offset in the same way as we did with the 0-page. So we can add X to the absolute value we specified by just putting a comma and the X after the address, or we can do the Y after the address with a comma. And so just as before, the address we specify plus X will be the address we end up reading from. And the same with Y, we'll just end up reading from the address plus Y, and that will be the result we will end up loading. So let's try that out. So we've done our example here, and you can see we loaded in from 2000 here, and X was 1, so we ended up loading from 2000 plus 1, which is 1B. You can see that here. When we used the Y register, Y was 2, so we ended up loading from here 1C. That's 2 after the address 2000. So you can see that works just fine. And actually, unlike the 0-page option with Y, this option does have a lot of abilities for the Y register version, but still not as many as for the X version. Now that's all very well and good, but there will be times where we need to be able to change the way things work, and we might want to be able to store an address at another address so that we can kind of do 2 hops to our destination. Now with the 6502, there is a special command that allows us to do this. It's called absolute indirect addressing, and let's have a look at it now. Now, absolute indirect addressing strangely works with just a single command. So what we do is we use one memory address to store a second one, and it's that resulting second address that is used in our command. We can only do it with the jump command. Now I've said before that 6502 is a little endian system, and this is quite important at this point, so let's have a look at it here. So we can only use this with the jump command, and what we do is we put brackets around the address we want to use. So if we specify to jump to the indirect address hexadecimal 2000 using these brackets, what happens is 2 bytes are read from address 2000 and 2001. These are used in opposite order to produce another address. So if we loaded in 1A and 1B, the resulting address would be 1B, 1A, and then a jump is made to that resulting address. So rather than jumping to the address 2000, putting the brackets around the address has resulted to jumping to the address in to address 2000. And that's why it's indirect, because there's an extra stage in there. Now, to be honest, this isn't a command I've actually come across using just yet. It's a great command, and I'm sure it's got lots of great uses, but it's not one that's that important. As with a lot of the things, if you don't understand it at this stage, please don't worry about it, because you can do lots and lots of stuff before you'll ever need to worry about this. And at the point you do need to worry about it, you're probably going to start understanding it. So don't worry about that too much. So let's try this command out then. So what's happened here? So we've jumped indirectly to the address at memory address 2000. Well, what address is at 2000? Well, in little endian it's 1B, 1A. And we did load some bytes into memory address 1B, 1A here. There was a 69 here, which was just a test byte, and then we've got all of these bytes here. So let's have a look at what we actually loaded in. Well, what we actually loaded in is these commands here. So there was a byte db69, and this was intentionally bad data to prove we weren't actually hitting this address. But then all we were doing is we were doing an execution of the monitor command, and then going into an infinite loop. Now, it's a bit technical at this point, but I've used BBC here because this is a relative jump, and this is what's known as relocatable code, because it's running at a different memory address than in the actual source. Don't worry about that if you don't know what it means. It's very complex. I just wanted to explain it as we were passing. So effectively, that this is just executing the monitor. We can confirm that that has actually happened, because if you look here, the P register here is the program counter, and we are currently running at address 1B, 1C. And so the current program counter is currently here, which is the end of the call to the monitor. Now, byte 69 was never executed because we jumped to 1B, 1A, and so we skipped straight to here. If we'd have executed this, it would have probably caused some trouble. But anyway, the point I'm making is we've jumped indirectly to the address here because that address was stored in the 2000 that we indirectly called in our source code just here. So there we go. Indirect addressing is far more important when it comes to using the 0 page and the X and Y register. So as I've said before, we don't have many registers to work with, so we need to make the best of the ones that we've got. And when it came to the Z80, we could use HL and DE to store addresses that we wanted to read from or write to. We can't do that on the 6502. So what we do on the 6502 is we store an address that we want to work with in the 0 page, and then use the indirect commands on those addresses, and the address held in that area of the 0 page will have the commands effectively executed on them. Now, that's not a great way of describing it, I apologize, but it will become more clear if we look at the example here. So if we do a load of open brackets hexadecimal 80 comma X close brackets, what happens is the value in X, which in this case is 1, is added to that 0 page hexadecimal 80, giving a resulting address of 81. 2 bytes are read in little endian order, so they are reversed, and they produce an address. So 1213 will produce an address of 1312. Now, because it's indirect, we then read from that resulting address and we get the value to use in our command. So this will effectively be loading A with hexadecimal 31, and it's this bit here that's the indirect part. Again, I know this sounds confusing, and it unfortunately is, but you'll get very used to using this command very quickly and you'll forget what it's actually doing. Effectively, you're just using hexadecimal 80 as a store for an address. That's really all it is, and you can just forget about the rest. You'll see very quickly how it works. So let's have a go with that in our example here. So to start with, we're going to load X with 1, and then we're going to read in indirectly from the 0 page hexadecimal 80 comma X. So let's execute this and see what happens. So it's hexadecimal 80, we had the values 11, 12, 13. Now X is equal to 1 here, so we read in from hexadecimal 80 plus 1. So we're reading in 12, 13. And these make the address 1312. And at 1312 is the value 31. So we ended up with A equals 31 because that X was being added to the indirect address would be read from, and then the bytes are reversed because it's little endian. So I know that's a little bit confusing, but just bear with me. So we can just try that again in a different way. If we now change this to 0 and this to 81, and then we run it again, you will find that the result is actually the same. Well, why? Because remember, we were directly adding X to the value here. So if this is 1 and this is 80, or this is 81 and this is 0, the result will be the same. What will change the result is if we change this to 2. Well, why is that? Let's look what happens. Well, so we're now reading in from hexadecimal 80 plus 2. So we're now reading in from memory address 1413. And I've not set any data in this example, so that's just 0. So that's how you can use the X register to perform indirection on the 0 page. And it's only the 0 page that can do this, which is why the 0 page is so important. Now, as I've said before, you might not understand that example. Don't worry about it too much. We're going to come back to all of this later. And when you actually see it in examples of things you want to do, you'll start to understand how it works and why. So for now, just kind of remember this in the back of your memory so that if later on you need to see this in a practical case again, just come back to these examples then, and it should help you at that point. It's very difficult at this theoretical stage to explain these commands, but it's very difficult to use the commands unless you've explained them first. So as I say, just please bear with me on that. Now, in my experience, I don't tend to use that command really at all, but a very, very important command is the post-indexed addressing with Y. Now, in the last case, we were adding X to the 0 page address, but that's only useful if we want to read from a range of 0 pages. What's much more useful is to use an address held in the 0 page and then read from consecutive addresses of that address. And we can use this for things like LDIR, copying banks of memory and things very quickly. So how does this work? So we're loading from 0 page address hexadecimal 80 with Y as a post-indexed indirect address. And how does this work? Well, 2 bytes are loaded in from the 0 page we specified, hexadecimal 80. They become an address, little endian, so they're reversed. So that address becomes 1211. And then at that stage, the Y is added. So whereas we were adding X at the start before, we're now adding Y at the end. So that Y becomes an offset to that final address. And so by consecutively changing Y, we can use that temporary store of an address to read from consecutive addresses. Again, I know that's a little bit confusing and we are going to come to it later. But let's have a look at it in this example now. So we're going to load Y with 2. We're then going to load in A from hexadecimal 80 in the 0 page, offset with Y. And let's see what actually happens. So here's the example running. So you can see here that in hexadecimal 80 we had the memory address in little endian 12111. So here's 12111, and then 2 were added to that because Y was 2, and so we ended up loading in the value 42 here. So obviously life, the universe and everything, I suppose. So we can try that again if we just change it to 1. Well, now the same memory address was read in here, but this time we've loaded in 41 here. And if we change it to 0, maybe you can guess, we're going to end up with 40. So just by consecutively changing Y, we're changing the destination address that's read in, and effectively these bytes here are a temporary holding of the address we're working on. And so if you're familiar with Z80, we're effectively using this address like a HL or a DE, and we're going to come to that later. But if you don't know Z80, don't worry about it. Again, just if you can try and play around with these examples and just understand the way that Y is affecting the address that's being read from, or written to, of course, because all these commands work with reading and writing. Hopefully that will make some sense to you. But anyway, let's carry on. So there's one more special mode that we do want to discuss. This is one you probably won't be able to use, but we're going to discuss it anyway. Now, we had a look before at absolute indirect addressing here, and of course that could only be used with the jump command, but there is on the more advanced processors, because the 6502 had a successor called the 65C02. It's used by the Atari Lynx, the Super Nintendo, the PC Engine and the Apple II, but all the other systems like the C64 don't have it. But I want to discuss it anyway. And what this does is it uses 2 bytes in the 0 page in the same way as the absolute indirect worked for the jump command. This will work for any command, give or take. So how does this work? Well, it's very simple really. Basically 2 bytes are read in from the 0 page. These form an address, again in little endian, so they're backwards. So 1213 becomes address 1312, and the result that's used in the command is read from that resulting address. So very straightforward, and let's see that in action. So we can't use this on the BBC, but we can run it on the Apple II. So here you can see we loaded in from hexadecimal 81 in the 0 page, so we loaded in address 1312 here. So 1310, 11, 12, so we've read in 31 here into our accumulator via that indirect address here. Well, this is actually a really good command, but as I say, we don't have it on most of the systems we're going to be covering in these tutorials. But don't worry, we can fake it. What we can do is if we do LDY #0 and then put the Y here and execute this, the result is the same. And we can also do LDX #0 and put X here And we've done the same. So effectively we can use 2 bytes of the 0 page as an address and then read from that address directly just by setting X or Y to 0. And we're going to be doing this a lot when we come to more complex programming in 6502, because although this indirect command is really good, unfortunately the vast majority of the systems we're going to be looking at don't have it, so we won't really be using it. But it's of course worth you knowing about, and if you're looking to program exclusively for the Apple II and the Lynx and the SNES and the PC Engine, you know, go ahead and use it because it's a good command. It's just rarely available to us. So there we go. So that's actually all of the commands I wanted to discuss today. I know they're very confusing, and as I've said before, don't be too scared if you don't understand them yet, because in a lot of ways you don't really need to know how they work. You just know how to use them and what they do. And you know, even myself looking at these commands, sometimes it looks a bit daunting what they're doing, because once you actually get used to how you use them in programming, the theory behind them becomes kind of irrelevant, and it's just a case of making use of them. But at an early stage, I think it was important to at least give a example of where you could see these working, and hopefully the charts here with these arrows and things will make it a little bit clearer to you. And of course, play around with the examples if you want. Just remember, they only are guaranteed to work on the BBC because of writing to various hard memory addresses that might be in use on other systems. Anyway, I hope you've enjoyed today's lesson. If you have, please like and subscribe. Also, definitely go to the website, download that cheat sheet, because I rely on this all the time with my 6502. I actually have this printed out and the 68000 version on the other side, and I have it laminated, and I never program without it right by my side, because it really is key if you're learning or you're not sort of fully experienced with 6502 assembly and you just need to quickly check which commands do and don't exist. You'll notice some of them in green. These are the ones that are only available on the 65C02. For example, the PC Engine, the Atari Lynx, the Apple II. There were also some in red. These are only available on the PC Engine because that's even more advanced. That's a custom chip for the PC Engine that has commands nothing else has. But the basic black commands are available on all 6502 systems. If you want to play it safe, just don't use anything that's not in black on your programming. Anyway, hope you've enjoyed today's lesson. Thanks for watching and goodbye.